Welcome to GATE video lecture. I am Lavanya, Department of Mathematics, S.A.ENGG.COLLEGE. In this video, we are going to discuss about the vector space in linear algebra. Before going to the topic, we'll start with the introduction part. Introduction of vector spaces. Vector space is a collection of objects called vectors which may be added together and multiplied by numbers is called a scalar. In this vector space we are using in many fields like mathematics, science and engineering. Okay, before that we are start with the sets. So set is a well defined objects. Okay, in this we are going to discuss about the set of natural numbers, set of integers, set of real numbers, set of complex numbers. Then binary operation. Star is a binary operation. It is denoted by S, star. Then group. Group is nothing but a non-empty set, and star is a binary operation on G. G, star is the group. In this we are going to solve some more properties like closure property, associative property, existence of inverse. Closure property means A star B belongs to G for all A, B belongs to G. Associative property means A star B star C equal to A star B star C for all A, B, C belongs to G. Existence of identity means there exists E belongs to G such that A star E equal to E star A equal to A for all A belongs to G. Existence of inverse means for all A belongs to G there exists A inverse belongs to G such that A star A inverse equal to A star A inverse star A equal to E. Then we will discuss about the vector space definition. So what is mean by vector space? Vector space is a V over a field F consists of set of on which two operations are defined. Vector addition which associates with each pair of vectors x, y belongs to V. There is a unique element x plus y belongs to V. And then scalar multiplication, each scalar A belongs to F and x belongs to V. There is a unique element Ax belongs to V such that the following conditions are holds good. In this form, an object of form A1, A2 and so on An whose entries A1, A2 and so on An are the elements of F is called the n multiple. Then Fn is denoted by set of all A1, A2 and so on An such that A1, A2 and so on An belongs to F. The F2 is ordered pair A1, A2 such that A1, A2 belongs to F. F3 is ordered triplet A1, A2, A3 such that A1, A2, A3 belongs to F. Then these conditions should hold good for the vector space. First condition is for all x, y belongs to V, x plus y equal to y plus x. It's a commutative under addition. Then three elements we are choosing. For all x, y, z belongs to V, x plus y plus z equal to x plus y plus z. So associative under addition. Third one is there exists an element 0 belongs to V such that x plus 0 equal to x for all x belongs to V. Here 0 is the identity element. Then for each vector x belongs to V, there is a unique vector minus x belongs to V such that x plus minus x equal to 0. Then fifth condition is for all x belongs to V, 1 into x is equal to x. Sixth condition is then multiply with the scalars ab into x equal to a into bx for all a, b belongs to f, x belongs to v. Seventh condition is a into x plus y equal to then ax plus ay for all a belongs to f, x, y belongs to v. Last condition is a plus b into x equal to ax plus bx for all a, b belongs to f, x belongs to v. Then we will discuss the problem. First problem is set of all ordered pair F2 is a vector space over F with the operation coordinate wise addition and scalar multiplication. In this problem we are going to discuss the set of all ordered pair in F2 satisfies the vector space or not. First we have to check whether all the 8 conditions. If it is satisfied we can say that the ordered pair of F2 is vector space. Okay, solution for this is let V be the set of all ordered pairs, that is V equal to F2. We are considering the two scalars a1, a2 such that a1, a2 belongs to f. Define addition a plus v equal to a1 plus b1, a2 plus b2 belongs to v. Scalar multiplication cu equal to ca1, ca2 belongs to v. Now we are going to prove v is a vector space. We shall prove v, plus an abelian group. Abelian group means A into B equal to B into A, or A plus B equal to B plus A, under addition, and that is under multiplication. First one is closure property. For all u comma b, v belongs to B, u plus v equal to A1 plus B1 comma A2 plus B2 belongs to F2. Since A1 plus B1 comma A2 plus B2 belongs to F, F is a field. Then second property, associative property. Here we are considering three elements. For all u comma v comma w belongs to V, then W is equal to C1 comma C2, that is also belongs to F2. Now we are considering three elements, U plus V plus W is equal to, here U is A1 comma A2, V is B1 comma B2, W is C1 comma C2. Now we are combining these two, we'll get B1 plus C1 comma B2 plus C2. Now combination of these two we are going to take. That we'll get A1 plus B1 plus C1 comma A2 plus B2 plus C2. Then combine these two, A1 plus B1 plus C1 comma A2 plus B2 plus C2 is the associative under addition. So finally we are getting U plus V plus W. Then next one is identity. 0 comma 0 is an identity element. 0 belongs to F, so that 0 comma 0 is, that is ordered pair, that is also belongs to F. V. U plus 0 is equal to A1 comma A2 plus 0 is nothing but 0 comma 0. When you add up these two, we will get A1 comma A2 is equal to U. Next one is inverse. If U is equal to A1 comma A2 belongs to V, then minus U is nothing but minus A1 comma minus A2. Since A1 comma A2 belongs to F, similarly minus A1 comma minus A2 is also belongs to F. Now we are adding these two, that is U plus minus U, will get what? 0. So we can say that minus U is an additive inverse of U. Then commutative property. Commutative property means we have to prove U plus V is equal to V plus U. So U plus V is equal to, what is U? A1 comma A2 plus V is B1 comma B2. When adding these two, will get A1 plus B1 comma A2 plus B2. This we can interchange and write B1 plus A1 comma B2 plus A2, since F is a abelian group under addition. Therefore, we can say that B comma plus is an abelian group. Second conditions under scalar multiplication. So here first property, for all u comma v belongs to B and alpha belongs to, A belongs to F, A into u plus v equal to A into A comma A2 plus B1 into B1 comma B2. Then A into A1 plus B1 comma A2 plus B2. Here A into A1 plus A into B1, A into A2 plus B into B2. Then combine these two, will get AU plus AV. Then second property, for all A comma B belongs to F, U belongs to B. Then consider A plus B into U, that is equal to, here U is nothing but A1 comma A2. Then A plus B into A1 comma A plus B into A2. Then multiply inside of these terms, A into A1 plus B into A1 comma A into A2 plus B into A2. Then combine this, we'll get A into A1 comma A into A2 plus B into A1 comma B into A2. Then we'll get AU plus BU. That property is satisfied. Second one, for all A comma B belongs to F and U belongs to V, then consider AB into U. AB into U is nothing but A1 comma A2. Then multiply with these terms. So AB into A1 comma AB into A2. Then combine this, A into B into A1, A into B into A2. Then A is the common term, take it out. BA1 comma BA2. Here also B is the common term, take it out. B into A1 comma A2. A1 comma A2 is nothing but U. So AB into U is equal to A into BU. Then second one, for all 1 belongs to F and U belongs to V, 1 into U is equal to, 1 into U is nothing but A1 comma A2. That is equal to U. So therefore, we can say that P is equal to F is a vector space over F, because 8 properties it satisfied F2. So we can say that B is a vector space. Then come to the next problem. V be the set of all 2 by 2 matrices with real entries. Show that V is a vector space over F with respect to usual matrix addition done entry wise and usual scalar multiplication done entry wise. Verify all the conditions of the vector space. Now we are going to check whether 2 by 2 matrix satisfies the vector space conditions or not. So solution for this, V be the set of all 2 by 2 matrices with real entries. We are considering B is equal to M 2 by 2. A is nothing but A11, A12, A21, A22, such that A11, A12, A22, A21, A22 belongs to R. Can define for all A is equal to 2 by 2 matrix A11, A12, A21, A22. B is equal to B11, B12, B21, B22 belongs to V. C belongs to R. Addition for this, A plus B equal to A matrix and then B matrix. Combine these two will get A11 plus B11, A12 plus B12, A21 plus B21, A22 plus B22. That is also belongs to D. Then scalar multiplication. C into A. C is a scalar, A is a matrix, and multiply with these two will get C A11, C A12, C A21, A C2. A22 belongs to V. To prove V is equal to M 2 by 2 is a vector space. We shall prove V comma plus is an abelian group. First property, closure property. For all A comma B belongs to V, A plus B is equal to, adding these two matrices will get A11 plus B11, A12 plus B12, A21 plus B21, A22 plus B22. This also belongs to V. For all Aij comma Bij belongs to R. Second property, associative property. Here we are considering three elements, three matrices. A comma B comma C belongs to V. C is nothing but C11, C12, C21, C22. Then consider A plus B plus C. A matrix is A11, A12, A21, A22 plus B matrix is B11, B12, B21, B22 plus C matrix is C11, C12, C21, C22. Then first add these two matrices will get B11 plus C11, B12 plus C12, B21 plus C21, B22 plus C22. Then add these two matrices will get A11 plus B11 plus C11, A12 plus B12 plus C12, A21 plus B21 plus C21, A22 plus B22 plus C22. Then finally we can combine this will get A plus B plus C. Then third one is identity. Here 0 belongs to R, so that 0, 0, 0, 0, 0 belongs to V. Add with the matrix A will get A11, A12, A21, A22 plus 0 matrix. When you add up these two will get A11, A12, A21, A22 equal to A. Here 0, 0, 0, 0, 0, 0 belongs to V is an identity element. Then inverse. If A is equal to A11, A12, A21, A22 such that minus A equal to minus A11, minus A12, minus A21, minus A22 belongs to B. Therefore, minus A is the additive inverse element of A. Then commutative. For all A comma B belongs to V, A plus B equal to B plus A. Therefore, Aij, Bij equal to Bij equal to Aij. So, therefore, V comma plus is an abelian group. Then next condition under scalar multiplication. For all A comma B belongs to V and alpha belongs to R. So, consider alpha into A plus B, alpha into A matrix and then B matrix. Then add these two will get A11 plus B11, A12 plus B12, A21 plus B21, A22 plus B22. Then alpha multiply with these terms will get alpha into A11 plus alpha into B11 alpha A11, alpha A12, alpha A21, alpha A22 plus alpha B11, alpha B12, alpha B21, alpha B22. Then take alpha here outside, here also outside. This is nothing but A matrix, this is nothing but B matrix. We'll get alpha into A plus B equal to alpha A plus alpha B. Then next condition, for all alpha comma beta belongs to R and A belongs to B, then consider alpha plus beta into A is equal to alpha plus beta, then A matrix is A11, A12, A21, A22. Then multiply with these terms and get A alpha into A11 plus beta into A11, alpha into A12 plus beta into A12, alpha A21 plus beta A21, alpha A22 plus beta A22. Then we'll get alpha A plus beta A. Okay. Next one is for all alpha comma beta belongs to R and A belongs to B, alpha beta into A. Alpha beta into A matrix is nothing but this. Then multiply each term with alpha beta. Then take alpha outside, combine these two. Then from all these things, beta is a common term, it's nothing but A matrix. So alpha beta into A is equal to alpha into beta A. Then last one, for all 1 belongs to R and A belongs to B, 1A is equal to 1 into A11, A12, A21, A22 is nothing but A. Therefore, we can say that B is equal to M22 is a vector space over R. So 2 by 2 matrix satisfies the vector space conditions. Then polynomial. What is mean by polynomial? With coefficient from a field f is an expression of the form f of x equal to an x power n plus an minus 1 x power n minus 1 and so on, a1x plus a0. Now we are going to show that this polynomial satisfies the vector space conditions or not, whether this polynomial is a vector space or not. So solution for this, B be the set of all polynomial of degree less than or equal to n over the field f. So V is equal to polynomial is denoted by P of f is nothing but f of x equal to an x power n plus an minus 1 x power n minus 1 plus and so on a1x plus a0, such that all the scalars a0, a1 and so on an belongs to field f. Now define the vector space. For all f of x comma g of x belongs to P of f. F of x equal to an x power n plus an minus 1 x power n minus 1 plus and so on a1x plus a0. G of x is bn x power n plus bn minus 1 x power n minus 1 and so on b1x plus b0. Then addition for this case, consider two polynomials f of x plus g of x equal to an plus bn x power n plus an minus 1 plus bn minus 1 x power n minus 1 and so on a1 plus b1 into x plus a0 plus b0. Then scalar multiplication, c into f of x equal to c into an x power n, c into n minus 1 an minus 1 x power n minus 1 and so on c into a1x plus c into a0. Now prove the 8 conditions. V is equal to P of S is a vector space. That only we are going to prove. We shall prove V comma plus is an abelian group. First property is closure property. For all A, f of x comma g of x belongs to P of f, then addition of these two f of x plus g of x is equal to an plus bn into x power n, an minus 1 plus bn minus 1 x power n minus 1 and so on, a1 plus b1 into x plus a0 plus b0. For since ai comma bi belongs to f, ai plus bi belongs to f. Then associative property. For all f of x comma g of x comma h of x belongs to P of f, h of x is equal to cn x power n plus cn minus 1 x power n minus 1 and so on c1x plus c0. So f of x plus g of x plus a combination of these two, then an x power n plus an minus 1 x power n minus 1 and so on a1x plus a0 plus g of x values bn plus cn x power n plus bn minus 1 cn minus 1 x power n minus 1 so on b0 plus c0. Then combine these two first, you'll get an plus bn plus cn into x power n, an minus 1 plus bn minus 1 and so on cn minus 1 x power n minus 1 and so on a0 a1 plus b1 plus c1 into x plus a0 plus b0 plus c0. Then an plus bn plus cn into x power n plus an minus 1 plus bn minus 1 plus cn minus 1 into x power n minus 1 and so on, we'll get a0 plus b0 plus c0. Then finally we can combine this, we'll get f of x plus g of x plus h of x. Next one, identity. 0 of x is the identity element of P of x. So 0 belongs to f, so that O of x belongs to P of x. So O of x plus f of x equal to f of x. Inverse, if f of x equal to an x power n plus an minus 1 x power n minus 1 and so on a1x plus a0, then consider minus f of x. Minus f of x is minus an x power n minus an minus 1 x power n minus 1 and so on minus a1x minus a0 belongs to P of f. Since a1, a2 and so on belongs to f, minus a1 minus an also belongs to f. So consider f of x plus minus of f of x. When you add up these two, will get 0 of x. So minus f of x is the additive inverse of f of x. Then commutative property. F of x plus g of x equal to an plus bn x power n plus an minus 1 plus bn minus 1 x power n minus 1 and so on. a1 plus b1 into x is equal plus a0 plus b0. Then combine, interchange these two. bn plus an x power n plus bn minus 1 plus an minus 1 x power n minus 1 and so on, b0 plus a0. Then multiply with those terms, you will get bn x power n plus bn minus 1 x power n minus 1 plus and so on, b1x plus b0. Then an x power n plus an minus 1 x power n minus 1 and so on, a1x plus a0. It's nothing but this is f of x, this is g of x. Therefore, p of x comma plus is an abelian group. Then condition under scalar multiplication. For all f of x comma g of x belongs to p of f, a belongs to f. Then a into f of x plus g of x. So a into f of x is nothing but an x power n minus 1 and so on, a0. G of x is nothing but bn x power n and so on, b0. Then add up these two, a into an plus bn into x power n minus n plus a into an minus 1 plus bn minus 1 x power n minus 1 and so on, a into a0 plus b0. Then club these two, will get a into f of x plus b into a into g of x. Then next condition, for all a comma b belongs to f and f of x belongs to p of f. A scalars a plus b into f of x equal to a plus b into f of x values an x power n plus an minus 1 x power n minus 1 and so on, a0. Then a plus b into an x power n plus a plus b into an minus 1 x power n minus 1 and so on, a plus b into a0. Then multiply with each terms. So a into an x power n, a into an minus 1 x power n minus 1 and so on, a into a0. Similarly, b an x power n plus b n minus 1 x power n minus 1 and so on, b into a0. This is nothing but a plus b, f of x is nothing but a into this is f of x plus b into this is g of x. Then for all a comma b belongs to f and f of x belongs to p of f. ab into f of x equal to ab into f of x is an x power n plus an minus 1 x power n minus 1 and so on, a0. Here ab into each term we have to multiply. So ab into an x power n plus ab into an minus 1 x power n minus 1 and so on, ab into a0. Then club these alone. So a into b an x power n plus a into b n minus 1 x power n minus 1 and a into b a0. Then a into b is nothing but f of x. So ab into f of x is equal to a into b into f of x. Then condition, last condition, for all 1 belongs to f and f of x belongs to p of f. 1 into f of x values an x power n plus an minus 1 x power n minus 1 and so on, an x plus a0 is nothing but f of x. So all 8 axioms is satisfies. We can say that V is equal to p of s in vector space over a field f. Then some elementary properties of vector space. So first theorem, cancellation law for vector addition. If x comma y comma z belongs to V such that x plus z equal to y plus z, then x is equal to y. Proof for this, let B be the additive inverse of z, then z plus b equal to 0. Therefore, x is equal to x plus 0. Instead of 0, we can replace z plus b. Then combine these two, so x plus z plus b. The x plus z is nothing but what, y plus z plus b. Then y plus, combine these two, z plus b. So z plus b is nothing but 0. So y plus 0 is equal to y. So we can say that x is equal to y. Then theorem 2, additive identity element of E is unique. Proof for this, let E comma F are two additive identity element of B. For x belongs to B, x plus E equal to E plus x is equal to x. Take this as equation number 1. Then x plus F is equal to F plus x is equal to x. Take this as equation number 2. From 1 and 2, x plus E equal to x plus F. Then x will go off by left cancellation law. So E is equal to F. Therefore, additive identity element of B is unique. Then third theorem, additive inverse element of V is unique. Proof, let y comma y dash are two additive inverse element of x belongs to V, then x plus y equal to y plus x is equal to 0. Similarly, x plus y dash equal to y dash plus x is equal to 0. Then solve these two equations, we will get x plus y equal to x plus y dash. By left cancellation law, x will go off, so y is equal to y dash. Therefore, additive inverse element of V is unique. Then theorem 4, prove that in a vector space V of f, we have 0 into x equal to 0 for all x belongs to V, 0 belongs to f. Second one, minus a into x is equal to minus ax equal to a into minus x for all a belongs to f, x belongs to B. Third one, a into 0 equal to 0 for all a belongs to f, 0 belongs to B. Then proof for the first one, 0 into x is equal to, in the place of 0 we can add 0 plus 0 into x. Then multiply with this 0 into x plus 0 into x. Then 0x equal to 0x equal to 0. Then 0 plus x into 0 plus equal to 0x plus 0x from 1 and 2. So you can say that 0x equal to 0. Then second one, for all a belongs to f, there exists minus a belongs to f, 0 belongs to f. We know that 0x is equal to 0. That's first condition. This implies a plus minus a into x is equal to 0. Then multiply x with these terms. Ax plus minus a into x equal to 0. Therefore, minus a into x is the inverse of ax. That is, minus a into x is equal to minus of ax. Similarly, a into minus x is equal to minus of ax. Therefore, minus ax equal to minus of ax equal to a into minus x. Then consider a into 0 equal to a into 0 plus 0. A into 0 plus a into 0, take this equation number 1. Then a0 equal to a0 plus 0. Equation number 2. From 1 and 2, a0 plus 0 equal to a0 plus a0. By right cancellation solve, we get a0 equal to 0. Thank you. We'll continue in the next session.